The next thing we have to talk about here in chapter 8 is including something into these problems, into these rigid body problems that should be very familiar, and that is friction. As you probably remember, friction comes in two types. We talk about kinetic friction also known as sliding friction or static friction, which is also known as static friction. Okay, how this works, you've all seen the simple example in physics somewhere along the line, I'm sure. If you've got a block on a surface, there's friction between the block and the surface. You have some pulling force here. Okay, this block has a weight, force due to gravity. There's a normal force from the table, and then friction opposes this motion. Call that force of friction. Okay, the idea here is if the pulling force is larger than the force of friction, it'll start moving. Okay, and then once it is moving, kinetic friction will kick in, and we'll be able to determine the acceleration of the block. Okay, so if you remember, static friction, force of friction, static is, and this is an important detail, is less than or equal to mu, the coefficient of friction, S for static, times n. Okay, the idea here is it's less than or equal to this value. Okay, so if P in this diagram is less than mu n, we're not going to have force of friction equal mu n. Force of, say, the pulling force is 100 and mu n equals 150. Okay, if we set 100 here and 150 this way, the reality is this block would be accelerating this direction. Friction doesn't work that way. Friction will go up to this value as much as it needs to prevent motion. Okay, if the pulling force exceeds the maximum friction value for static friction, then it starts moving. Once it starts moving, static friction goes out the window, and we have the force of kinetic friction with a K, which is equal to mu K times n. Okay, because if we're moving, friction's always going to resist that motion with as much force as it can. Okay, if we're not moving, friction is going to act with as much force as it takes to keep it from moving until the point where we manage to overcome that frictional force and break loose. Okay, so we'll go through a couple of examples here. And there is something that will kind of apply to a rigid body that will make this a little more complicated than what we're used to. Start with something fairly simple. I have two blocks connected by a string, cord, whatever, and we're pulling this way with, say, I'll use the actual values here. Actually, we'll find this value. This is our force P. Okay, I'm going to say these are both 50 kilograms. All right, this angle is given as 30 degrees. We'll keep it simple. And the coefficient of static friction is 0.25. And that's for both cases. All right, we have two objects here. We're going to have to, again, in general, you want to draw a free body diagram of each individual object. So we'll draw the block on the left. It's going to have a weight. It's going to have a normal force. It's going to have, pulling to the right is going to be the tension in the string, T. And pulling to the left is going to be our force of friction. Okay? Force of friction, and this is static for the case when it's not moving. Okay, I'm going to phrase this very carefully here. This is going to be find P, find the minimum P, value of P, for impending motion. Okay, this idea of impending motion is very important when it comes to static friction. Okay, this is a statics course. We're really not going to be dealing with kinetic friction because once something starts moving, it becomes a dynamics problem. Even if it's a simple dynamics problem, you could solve in physics along the way somewhere. But we're going to be dealing with static friction, and the idea here is we keep things stationary. Okay. Impending motion means we take P just up to the so it just equals the maximum value of friction. So friction has to act at its maximum value to keep it from moving. That's what we mean by impending motion. The idea that we're pulling as hard as we can without causing motion. If we pull with just some infinitesimal amount more, we're going to break loose, it's going to start moving, it's no longer a static problem. So that's what we mean by impending motion. Okay, so we have this diagram for this block. For the other block, the free body diagram is going to be a little bit different. We're still going to have weight, and it's still going to have a normal force. We're going to have this pulling force P up at 30 degrees above the horizontal. Acting to the left here, we have two forces. The string is pulling back, and we have a force of friction. Okay, so we have a couple of things going on here. We have, in this case, a couple of unknowns. This Fg is simply going to equal m times g, which is 50 kilograms times 9.8 meters per second squared, which is 490 newtons. So we'll do that. Normal force is going to be equal and opposite of the weight in this case, so this is also going to equal, let me take out the labels, I don't need them, 490, and I'll leave it in. Okay, force of static friction is, again, technically less than or equal to mu s times n. But because we're looking for impending motion, we're looking for the point where friction's reached its maximum, so it's not going to be less than, it is going to be equal to for the case of impending motion. So force of static friction is mu s n, mu s is given as 0.25, n is given, n we just found is 490, so that's going to be 122.5, just let me check, don't trust my math skills right now, 122.5. So this is equal to 122.5 newtons. So again, tension is pulling just as hard as this here. So tension is also going to equal 122.5 newtons. The idea here is we're pulling this system, or in this case, we're pulling on this block, which pulls on this cord, which pulls on this block. This block, if we pull 122.5, friction maxes out at 122.5. If we pull it less than 122.5, that's what friction will act as. If this tension is 80 newtons, friction will be 80 to cancel it out. If friction is 120 newtons, friction will be 120 to cancel it out. If tension is 122.5, friction will be 122.5 to cancel it out, but that's reaching its maximum value. If we go to anything larger than this, 122.6, 122.51, 122.5001 at the end, that's exceeding the maximum force of friction. We're going to start moving. Okay, so we call this the value for impending motion because it's the point where we've just reached our maximum, any tiny bit more than this, and we've started motion. So it's, again, impending motion. So these are our values here. We can bring the tension over. Okay, note that some of these values are going to be different over here. Okay, this block is going to have its own frictional force. This block's going to have its own weight, its own normal force, and this pulling force is new. It hasn't been applied to the other block. So the tension force here is going to be equal. It's the same cord, tension's the same throughout, so that's 122.5 newtons. Weight is easy. That's mass times acceleration due to gravity. We're going to get the same thing again. It's the same mass, 490 newtons. Okay. Now, Normal force is different, okay? The normal force is not just going to be equal to the weight because we have this upward component to our pulling force. So things are going to get a little bit trickier. All right, what I'm going to do is erase this piece. So this brings us to our old friendly equilibrium equations. So if I do summation of forces in the y equals, well, that's n plus p sine 30 minus fg. And that does have to equal 0 because we're talking about a case where it's not going to move up or down at all. Again, if we pull, again, there could be enough of a lifting force to actually lift this off the ground, but it will start sliding before it gets lifted. So this is what we're looking at here. So n equals fg minus p sine 30. Well, fg is 490 and sine of 30 is 0.5. So n equals 490 minus p over 2. Okay, so we have a value for n. Our force of friction here, and again it's going to be equal to, we're not doing the less than equal to thing because we are dealing with impending motion. Force of friction is mu s times n, which is 0.25 times 490 minus p over 2. Well, this becomes force of static friction here becomes 0.25 times 490, it's the same 122.5, minus p over 8. Okay? So friction is actually going to depend on how hard we're pulling. Again, because as we're pulling, we're going to lift this, we're going to take some of the weight off of the table, reduce the normal force, it's going to reduce our friction. Okay? So we have our normal, we have our force of static friction. Now we can do summation of forces in the x. Okay, I'm going to erase this diagram, we're done with it for now, and keep working over here. So I have normal, I have force of static friction, I have everything except this p value. Okay, so now I need to know that the summation of forces in the x are going to equal 0, i.e. we're looking for this p value where the horizontal component just barely is canceled by these pulling back, the 122 newtons of tension in the cable plus this frictional force here. Okay, we're looking again for the point where this just these two just barely cancel this. So we're going to go with 0 equals p times the cosine of 30 minus T minus force of friction static here. Okay, so we're going to have 0 equals P cosine 30 minus 122.5 minus 122.5 minus P over 8. Distribute the negative. We end up with 0 equals P cosine 30 minus 122.5 minus 122.5 plus P over 8. Okay, combined terms here. Actually, I'll bring these two over. So we end up with 245 equals P times cosine of 30 plus 1/8. Okay, bring the 122 over, bring the 122 over. So we have P cosine 30 plus P over 8. Factor out the P, we have P times cosine 30 times over 8. So P equals 245 divided by cosine 30 plus 1/8, 1.125. We can solve this. Is 247.2. Okay. So at this point, that means P has to be 247.2 newtons in order to get this block this system of blocks moving. Okay. So again, we can look at P here. We can say 122.5 minus P over 8. Well, P divided by 8 is 30.9. 122.5 minus 30.9 is 91.6. Okay, so that means pulling back here, we have 122. We just found this, if we actually needed it, was 91.6, 6 newtons. P is 257, but the x component times the cosine of 30 is 214.1. 122.5 plus 91.6 is 214.1. So the x component here is going to equal those two. We found out what kind of pulling force here is required for impending motion. Okay, this should all have been review, hopefully. Stuff you've seen before. But again, just being able to integrate friction into very basic style problems. Okay, we will take a look at another sort of classic problem, which is a ladder problem. So in a ladder problem, take a simple case. We've got a ground in the wall. Okay, we're going to take a ladder, say looking like this. Okay, so we're going to take that, say it has a weight that will act in the middle. Don't know exactly where that is yet. This has a length of 26 feet. All right, we're going to say contact here is smooth. Okay, when you hear the phrase smooth contact, that means negligible friction. We're not going to have any friction here. We are going to have friction down at the bottom. Friction at the bottom is going to be the coefficient of friction, μs of 0.3. Okay, so we've got this ladder here. It's resting up against the wall. There's negligible friction at the top, but there's friction at the bottom that's keeping it from sliding down flat onto the ground. Okay, the question here I have, I'll put this down a little lower. Is what is the maximum value for D so that the ladder doesn't slip? It does not slip. So obviously, as this thing gets flatter and flatter, eventually it gets to the point where it just slips and falls. We want to know where that would actually happen. All right, so the trick here is, again, the free body diagram. We have a smooth contact here, okay? Just like we talked about any other support forces, that's going to give us a force acting here. We call this point A at the top, point B at the bottom. So this will be A in the X. Point B, we also have a contact surface here, so we're going to have B in the Y. That's point B. B in the Y is the normal force holding it up. B in the Y is also the normal force. We're going to have friction acting to the left here. Okay? And at some point in the middle, we're going to have weight. So redrawing my free body diagram over here of just the ladder itself, I'm going to call this the normal at A, the normal at B. Oops, that should be horizontal. the force of friction, and then right in the middle, I have the weight, which is given as 30 pounds. Okay, so this is not terribly difficult. Okay, this just becomes a simple equilibrium problem. All right, well, we know the length of the ladder is 26 feet. The distance to the middle is obviously going to be 13 feet. All right, so what we're looking at now is trying to find what these values are. Okay, this is not an easy problem though because of the geometry. We have this triangle here. If we make this ladder into a triangle, we're looking for distance d here. We'll call this distance h to the top. They are obviously related. Okay, what I'm going to do here is I'm going to call this angle theta. Okay, if I know theta, then I can find h and d. Okay, just simply using trig. I know the length of the hypotenuse is 26, so using cosine I can find d, using sine I can find h, and we're not ultimately going to care about h, but I'll leave it there for now. So really what I'm looking for is to find this angle. If I find that angle, then I can work with the rest of it. And that allows me to do some things here in terms of distances. Okay, so I'm going to actually call this 26 cosine theta. I'm going to call this 26 sine theta. The reason for that is now I can actually only dealing with one unknown in terms of my geometry. Everything's in terms of theta. Okay. Again, these ladder problems look trivially easy, but they really aren't. So what I'm going to do here is I have an equilibrium problem, so I'm going to write my three equations of equilibrium. I'm going to do a summation of forces in the x. In the x, I have an A, normal force at A, minus force of friction. Easy enough. We also know that, again, as this thing gets closer and closer, we're again looking for the point of impending motion. If this thing is almost right up against the wall, friction's not going to have to work as hard as it can to keep it in place. As we get further and further out, it'll get to the point where it's working as hard as it can to keep the thing in place. If it moves just a tick more, it'll slide. So we're looking for the case where force of friction, static friction, is mu s times normal force at B. Because again, we have friction at point B, so it is a normal force at B that we care about. Okay, so we also have so I'm going to replace that here. NA equals force of friction is mu s times NB. Okay? We know mu s, we don't know NA or NB. Summation of forces in the y is equal to 0. Is equal to, well, that's just minus 30 plus NB. Well, that actually gives us something really useful. This tells us NB is equal to 30 pounds. We can now bring summation of forces in the x over and say, all right, 0 equals NA minus mu s was 0.3, I believe. Yep, 0.3 times NB is 30. So NA, the normal force at A, is going to be equal to 0.3 times 30 is 9 pounds. Okay, this is really useful. We can start substituting some of these values in. I'll write these over here. So this equals NB is 30. And A is 9. And if we care about this, it's 0.3 times 30. It's also 9 pounds, only it's acting in the opposite direction. If you want to label that -9, that's fine. But considering that the arrow already tells us our direction, I'll leave the negative sign. Okay, so that's what we get out of our summation of forces. We now know all of these. We've now been able to determine what all these forces are. The question is, well, how do we get theta? Well, theta is going to come from the summation of moments in this case. Okay, because these forces fully meet this conditions for equilibrium of forces. Okay, we don't know that they've met the criteria for equilibrium of moments. So I'm going to take moments about B here at the bottom. I think that's going to be the easiest way to do this, because this way two of our forces drop out. Okay, so what we're going to do here is we have summation of moments about B is equal to, okay, it is worth noting that these forces are only one of many, many set of forces that will meet these criteria for balance of forces. We're interested in this particular set where things are 30 vertically and 9 horizontally. This is the case, because remember we assumed this was equal, this is the case for impending motion. Okay, if we slide this in further, theta gets larger, so the frictional force gets smaller, this isn't going to be 9 anymore, things get a little different. But when the case that this is exactly 9, that's the case for impending motion. We did make this assumption of equality, which means we have already assumed we're in the case of impending motion. So we'll go ahead and solve this. So 30, its moment arm, okay, the moment about B equals 0 is equal to 30. That is going to go counterclockwise, so it is positive, times its moment arm is half of this distance d. So 26 cosine theta over 2. Okay, half of that distance. Plus, oh sorry, in this case minus, like this, yeah, just bring it down. Okay, minus, because NA is causing a clockwise moment, minus NA, which is 9, I'll substitute that in a minute, times its moment arm as the vertical distance is 26 sine theta. Alright, so we're going to end up with a sine term and a cosine term, that's alright. And then NA, I'll sub in the 9 for this. Okay, so I'm going to bring this over, so 9 times 26 is 234 sine theta is equal to 30 times 26 over 2 is 390. Okay, you will see this a lot in ladder problems. Combinations of sine and cosine, things that will reduce essentially to tangent. What I'm going to do here is rewrite this as sine theta over cosine theta equals, bring the cosine down, bring the 234 over 390 over 234. Sine theta over cosine theta is simply tangent theta. This equals 390 divided by 234 is 1.67. Inverse tangent is 59 degrees. 59.03. So call it 59 degrees. Alright, so that means for the case when this is just barely holding itself up, when friction is just barely holding it up, theta is 59 degrees. Okay? Well, that becomes pretty straightforward to take this to the end then. So this is 59.0 degrees. Now we can find what I was calling D earlier and had replaced. So this is simply D. D equals, what do we got here? D is 26 times the cosine of theta. Okay, theta is 59 degrees, so 26 cosine 59. Is 13.38, sure, feet. So the furthest you can place this ladder away from the wall before it starts to slip is 13.38 feet. This piece I erased with sine over cosine turning into tangent, that happens a lot in these ladder problems. You'll see tangent, the relationship between tangent and the coefficient of friction. You'll see a lot of sine over cosine reducing that. So you're going to have to look, you will, on a lot of these ladder problems, start seeing tangent relationships involving this geometry. Okay, so this, while a little bit more complicated than something you've probably seen before, is nothing conceptually that you haven't seen. There is one other thing that we have to deal with in terms of friction for rigid bodies as opposed to particles, and that is, comes out of this example here. I'm going to buy myself a little board space. You guys should know it's friction by now. If I have a barrel or something here, and we're just going to say it's 2 feet across, 4 feet tall. Okay, and say I have a pushing force on it here of, say it has a, okay, say it has a, I'm pushing on it on this corner with a force P, and it has a weight of 100 pounds. Okay, very similar to the first one we did. It's going to be find P for impending motion. Okay, well this looks like a pretty easy problem. I should give you the angle on that force. We'll just make this easy and make it a 3, 4, 5 right triangle. Okay. So find P for impending motion. Again, I'm going to buy myself some board space here. You guys know the directions by now. So this looks like, oh, I'm going to give you guys a coefficient of friction. You're going to need that. Mu s here is 0.5. Okay, so we can do a free body diagram. Okay, we have a weight that acts at the bottom. We have a normal force that acts from the, I'm going to do this a little differently. We have a weight that acts in the center of the object. We have a normal force that's applied here. Okay, we have a applied force here that is the pushing force. That has the little 3, 4, 5 bit on it. Okay, this is 100 pounds. I should just plug in the number. All right, friction. Okay, notice that I'm not drawing all these forces right in the center of the object. Okay, we're dealing with rigid bodies now, not particles. When we drew the box in the first problem, just had everything acting in the middle. We were treating that box as a particle at its center of mass. Okay, for this, I'm going to draw these forces where they actually act. Okay, the normal force on the bottom surface. The weight acting from the center of mass, the pushing force applied at this corner. Friction is going to apply across this bottom surface and be force of friction here. Okay, so this becomes pretty easy. Summation of forces, x and y. We may have to do a summation in a moment, but I don't think so in this case. So summation of forces in the x is equal to, it's equal to 0. Again, we're looking for impending motion, so we're maxing out force of static friction, but still having everything cancel. So 0 equals 4/5 of P minus the force of friction. Summation of forces in the y is 0. That gives us that it's minus 3/5 P minus 100 plus n. Okay, so, well, n, we'll solve this. I'll do that in a second. I'll show you why we need that. Well, we need to get rid of force of friction. So force of friction, again, in the case of impending motion, is equal to mu s. And so force of friction is equal to 0.5 times n. So we need to know what n is. Well, n is equal to 100 plus 3/5 p. So I plug that in here. Force of friction is equal to 0.5 times 100 plus 3/5 p. That reduces to 0.5 times 100 is 50, plus 3/5 times a half is 3/10, or 0.3 p. So our force of friction is 50 plus 0.3 p. Summation of forces in the x, we have 0 equals 4/5 p. I'm going to turn that into a decimal. So we're going to go 0.8 p minus force of friction is 50 plus 0.3 p. Distribute the negative. We have 0 equals 0.8 p minus 50 minus 0.3 p. 50 over 50 equals 0.8 is 0.5 p. P equals 100 pounds. Okay, this is 100% correct if the question is what amount of force would cause this block or crate or whatever I called it to start sliding. Okay, the reality though is this thing is not necessarily going to slide. It has another mode in which it could move. This thing could either slide or it can tip over. Okay, you can tip things over, obviously. In this case, we have to check for that. So we know for sliding is 100 pounds. Okay, unfortunately, there's no tricky, clever way to do this. When you have something like this in pending motion, you have to check to see how much force it takes to get it sliding, which is what we've done before and we're familiar with. We also have to check and see how much it takes to cause it to tip. Okay, which we'll take a look at here. I'll show you how to do that. Now, before we can do that, I have to kind of have you guys rethink how this works a little bit, how this free body diagram works. I drew the normal force as a single force acting right on this, on the center point. If this block is just resting here, that's fine. If you think about a block just resting on a table, okay, that table is not exerting a force on one point and balancing it. In reality, what you can think about is that table is pushing up against that whole surface. You can actually kind of think about it as a little bit of a distributed load. As the table holds the block up, it holds the block up across that entire surface. Okay, it holds that block up the entire surface. So when we draw this individual force, we're saying, okay, the force that's holding it up is evenly distributed across the bottom. This is just a distributed load. We'll replace it with a single force right in the middle, and that'll work fine for our purposes. The problem is that assumes that this block is being held up evenly across the bottom. As we push on the top here and this thing starts to want to tip, this distributed load starts not looking so even. We get a lot more of the weight being pushed on that leading edge, to the point where it actually starts to tip over. Am I drawing this right? When it's actually tipping over, now the normal force is all applied on this one corner. Okay, so as we start pushing and pushing and pushing, this normal force, where it's applied, okay, simplify this distributed load into a single point force, it's actually going to be shifted a little bit off to the right. Okay, so when it's resting flat, lying there and minding its own business, nothing's pushing on it, the normal force we can say is right in the middle. As we start pushing it sideways, okay, as it starts to get this tipping, as it starts to not actually start lifting off the ground, but as we push and we start to give it a little bit of a tipping impulse here, whatever you want to call it, this normal force starts shifting over here, basically counteracting the moment caused by this pushing force. Okay, if I take moment about one of these points, I'm going to have a pushing force, I'm going to have a moment causing clockwise rotation. This is going to shift until it counters. When it finally tips over, this normal force is going to be applied on this corner. That's really the key detail here, is that when this tips, this normal force is not applied in the middle anymore, it's applied on this edge. Okay? That's an important detail. So when you start talking about something tipping over, the normal force is going to be applied at the point it's tipping about. Okay, so understanding this, how this moves, that's important, but for solving the problems, really you just need to know the normal force is applied at the corner that it's going to end up tipping about. So now I have my new revised free body diagram, and I need to know if this thing's going to tip over. Well, I can take moment, I can do a couple of things here. I'm going to call this point A, because that's an easy way to do this. So if I take moment about point A, the normal force is going to drop out because it's applied directly at A. The frictional force is going to drop out. All I've got is this 100-pound force, the weight, and this block over here. Notice the coefficient of friction doesn't matter. It doesn't matter what the friction is between the table and the crate in order to tip it over, because we're not actually causing those two surfaces to slide against one another. We're tipping it over, which doesn't require sliding, which means the amount of friction doesn't matter. Friction's only going to play a matter, and friction's only going to factor in as to how much it takes to slide. So what we can do here is we can take a quick look, solve this out. Okay, we still know all these other forces. I'm going to take summation of moment about A. Okay, I could go through here and find some of these other things, but we no longer can use, this is actually really important, for tipping, force of friction does not equal USN. Important, important, important. Okay, the idea here is we're not impending motion sliding. Okay, when something is about to slide, that's when these are equal. This is not about to slide. This is going to tip. So this is not going to be true. Without this being true, we have no means of finding this force. Okay, so we cannot do summation of forces in the x, simply because we don't know what that force is going to be. We cannot do summation of forces in the y. We're going to have too many unknowns if we just look at forces. We're going to, rather than do that, just write this out. So summation of forces in the x is going to give us the same 4/5. It's going to be equal to 0, which is going to give us the same 4/5 P minus force of friction S. Summation of forces in the y is also equal to 0, is equal to minus 3/5 P minus 100 plus N. Okay, we have two equations. We have 1, 2, 3 unknowns. When we were talking about sliding, we could use force of friction equals mu s n, because they were equal when we were talking about something that was about to start sliding. When we're just dealing with something that's about to start tipping, we lose that third equation. We can't solve this system. We can't solve a tipping problem involved with just analysis of forces, which makes sense. For tipping, we're rotating. That means we probably have to factor in the moment. So that's what we'll do here. Okay, so after all that, we're actually going to be able to solve this problem. So summation of moment about A. That's the point we're tipping about. Okay, we can take, that has to equal 0 for the point where it's just about to start tipping. Okay, so we're going to have the 100, oops, we have geometry here, so this is going to be 2. And I've now completely redrawn this diagram over here, but that's fine. Okay, so we have 3 forces, well 2 forces, but one we're going to split into components. So we're going to end up with 3 terms in our moment equation. So we're going to have 100, actually this will be space. 100 is going to cause rotation counterclockwise about A, so that's positive, times its distance is 1. Okay, we have the x component of P is going to go clockwise, so that's minus. The x component is 4/5 P times, I didn't have enough space. I'll rewrite this. Summation of moment about A is equal to 0 is equal to 100 times 1 foot minus 3/5, oops, x component, sorry. X component is 4/5 P times its moment arm is 4. The y component is acting downward here. That's going to be counterclockwise about A. So that's plus 3/5 P. Its moment arm is 2. Okay? So we have this expression here. It's going to give us the value of P that's going to cause it to, that's going to have it on the verge of tipping over. So again, the impending tipping is how the formal phrasing goes on that. So we have 0 equals 100 minus 4/5 times 0.8 times 4 is, what's that, 0.3.2? So we have minus 3.2 P, 3.2, and this is going to be, sorry, 1.2 plus 1.2 P. Okay, I'm going to bring this negative 100 equals minus 3.2 plus 1.2 is minus 2P. P ends up equaling 50 pounds. Okay, so this is P for tipping. What we have here is we've now found that it's going to take 100 pounds for P to cause this thing to slide. 50 pounds for this thing to cause it to tip over. Meaning we start pushing on this block in this direction, this particular object. Once we push with 50 pounds, it starts tipping, once we push with anything greater than 50 pounds, it starts tipping over, which means we never get to the point where it starts sliding. This answer is wrong. When I ask you what's the value for P to cause impending motion, you have to check both. The lesser one is going to be the correct one. It takes 50 pounds to cause this thing to be on the verge of moving, and it is on the verge of tipping. So again, this is the one kind of new piece with friction, dealing with something that we actually have is a two-dimensional object. We don't do this in 3 dimensions in this course. In a two-dimensional object, where we actually deal with the rotation as well as the translation.